Okay, I hope you can all hear me. Thank you
Yeah,
very
sure.
much for the opportunity to speak. This is joint work with two folk from the University of Tours, Julian Condé and Andrew L.V. Price. Um, Hopefully you can now see the second slide. Is that correct?
Yes, we do. We see.
Okay, thank you. All right. So we'll begin with a very brief overview of enumerative combinatorics, which should be familiar to almost everybody who is paying attention. Um, so the idea is we have some combinatorial class, and throughout this talk, because it's so short, we're going to deal with something very, very simple, which is tilings of a strip of width 1. And we're interested in counting how many of them there are of a particular length. And classically, we consider our answer to be the generating function. We're happy if we get a generating function. And so there's a trivial or very straightforward example of tiling a strip with tiles of length 1 and 2. And then analytic combinatorics enables us to do something slightly different. It gives us full information of the growth of the counting numbers in this case through treating the generating function as a complex function of a complex variable and looking at its singularities. And in particular, we have results like the one on the screen, that if we have a unique dominant singularity for our generating function, and it satisfies some elementary criteria, then we can immediately write down the asymptotic growth of the coefficients. And so, for example, with our Fibonacci tilings with a generating function 1 over 1 minus z squared, this has a dominant singularity, which is a simple pole at the inverse of phi, and we can get the asymptotic straightforwardly from that. So this is all well known, and much more is known, obviously, about what we can do in this direction. So the question that I want to address is what happens if we relax the requirement that objects have integer sizes. And a natural motivating example is the following question. We are tiling a strip with tiles of length 1 and of length beta for some irrational beta. And we want to know how many distinct tilings there are of a strength of a strip of length x, given that we do the natural thing in this case and permit the final tile to be a partial one, as you might do if you were tiling a path or something. So this is a natural combinatorial question, and it clearly requires something slightly different from what we have in normal enumerative and analytic combinatorics. And the first thing we require clearly is a generalization of the idea of a generating function. So now we need to allow the exponents in the monomials to be irrational. And that's it, basically. There are some natural restrictions on the set of such exponents. They need to be well ordered. And we call these Ribbenboim series in our paper after Paolo Ribbenboim because he investigated these from a algebraic perspective mainly in the 1990s. And so now we have this concept of an irrational generating function, and things follow through remarkably straightforwardly. So, for example, if we're tiling a strip with either square tiles or tiles of length beta, then the generating function, the irrational generating function, will be 1 over 1 minus z to the beta. And the first few terms ordered by increasing exponent are given at the bottom there. So for example, there are 3 different tilings of length 1 plus 2 root 2. I should point out that at this point we're ignoring this possibility of final partial tiles. We'll come back to that shortly. Okay. We also have a slight problem with thinking about the asymptotics because the coefficients in an irrational generating function can fluctuate very wildly. So if we look, for example, at 7 consecutive terms there in tiling with square tiles and tiles of length root 2, there's only one way of tiling a strip of length 11 with square tiles, but there are 126 different ways of tiling the next valid length, which turns out to be 4 plus 5 root 2. And then 2 later, we're back down to only one way of tiling a strip of length 8 root 2. That's 8 tiles, 8 root 2 tiles. But this is relatively easy to address this particular challenge. Instead of counting the number of objects of a given size, we decide that we're going to look at the number of objects of size up to some given value. And so all the natural notation gets introduced at this point where we're using less than or equal to x to denote sets of objects up to size x. And the extraction of coefficients of the terms whose exponents are less than or equal to x and so on. Okay, in order to make progress on this, we need some understanding of the analytic properties of irrational generating functions, or Ribbenbouin series. Unfortunately, these are not too scary. As with an ordinary generating function, we have a radius of convergence, and these functions are analytic within the disk of convergence, except that we have a branch cut, which conventionally is on the negative real axis. Furthermore, we have an analogous result to Springsheim's theorem, so that if the coefficients are non-negative and the radius of convergence is finite and equal to rho, then there is a singularity at the point z equals rho. However, it turns out that working directly with Ribbenbouin series isn't quite what we need to do to get all this to work. And so we consider a transform of our irrational generating function in which we replace z by e to the minus s. And this gives us a generalized Dirichlet series. And so we call, if we're dealing with a combinatorial question, this is the Dirichlet generating function of our irrational generating function. And this transform, which we call the exponential transform, since we're putting e to the minus s in for z, maps the disk of convergence, the cut disk of convergence, I should say, into the right half plane, so to the right of minus log rho. And the transformed function, the Dirichlet series, Dirichlet generating function, is analytic to the right of its line of convergence, which is the line where the real value is minus log rho. And in particular, the circle of convergence of the irrational generating function is mapped to this line of convergence. So in particular, in the combinatorial case where the coefficients are non-negative, then a singularity at rho gets mapped to a singularity at minus log rho. And in order to get sensible answers out of analysis, it turns out that we need a slightly stronger condition on the scenarios that we consider. And we say that a class of irrational combinatorial objects is intrinsically irrational if its Dirichlet generating function has a unique singularity, which by definition will be at minus log rho, where rho is the radius of convergence of the irrational generating function. So in a sense, what's happening here is that the sort of spiral thing that's going on the left, helical thing, gets expanded out, and we just want a single singularity on the line of convergence. In contrast, if we have an ordinary generating function, objects of integer sizes, then the Dirichlet generating function is going to be periodic in the imaginary direction, and there'll be a singularity at minus log rho plus 2 pi ki for each k. So we have repeated singularities there, which is not what we want to deal with. One other thing to note is that we have a quite nice, sufficient condition for intrinsic irrationality. We don't have to look in detail at the Dirichlet generating function, but there's not time to look into that at the moment. And this is our main result, that if our class is intrinsically irrational, and as given radius of convergence, then we have something that looks very, very similar to our asymptotic formula that we had on an earlier slide. So here, obviously, the number of differences here. We've got x rather than n. We've got less than or equal to x rather than equals n. And there's an extra factor of log 1 over rho minus log rho in the denominator. But apart from that, everything turns out to be as before. Let's make a comment here that if we look at an irrational class that isn't intrinsically irrational, so there's multiple singularities on the line of convergence in its Dirichlet generating function, then we'll get periodic oscillations in the asymptotics. So such a formula as comes from this main result, where it doesn't apply. We also look into that in the paper we've written. So let's just conclude by having a look at some examples very briefly. So here's the situation for tiling with 2 tiles. The asymptotics given there. We can generalize this to any set of tiles which are not all where the lengths are not all multiples of some given value omega. We can handle the partial final tile thing by essentially throwing away the run of tiles of a particular color. So here I've got an example with 4 possible colors, and then we can extend this shortened tiling either with, in this case, a yellow, green, or red tiles, and this gives us a nice bijection which allows us to handle this partial tile scenario, which was the motivating example. We don't have to deal with things quite that simple here, and I will conclude with a slightly more complicated example here. So here we're going to have some forests of combinatorial trees where we allow certain vertices, the root and the leaves, to have one of 2 different sizes, one of which is irrational. Coming up with the irrational generating function is very straightforward. But the asymptotics have three phases here, depending on the values of beta and gamma, two different sizes, and with distinct critical exponents. Going along with that, unsurprisingly, the number of trees in a forest also is going to, well, the asymptotics are going to depend on the value here of gamma. Now we've got a linear number of trees. If gamma is less than 1, we've got the square root number of trees growing like the square root of x if gamma is equal to 1, and a constant number of trees if gamma is greater than 1. So that's a very, very, very quick introduction to what I believe is a useful extension of the theory of analytic combinatorics. Thank you.